I got no power cord today at the moment, so we're on battery power, hopefully. I've also only got 102 minutes worth of space on there. No, an hour and 2 minutes, so I cannot go over more than 2 minutes unless I want to say politically incorrect things, which are not recorded, in which case I can talk for another 5, But it's safe for me to do that because there's just not even space on the camera today. All right, I'll start. Dear Father, we thank you for this day. I thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. Okay, so let me get started on a picture. So we're talking about the Laurent decomposition. And so roughly speaking, the picture is something like this. Or at least this is an interesting picture. I mean, in practice, the inner circle could be at 0, so it could either just be a deleted point or even just everything deleted. And the outer circle could go to infinity. These are possibilities. So we said that the inner radius was rho, the outer radius was sigma. And last time I argued that there is a Laurent decomposition, which is what? So you're given F is analytic, aka holomorphic, between the circles, right? And then and of course, like I just said, 0 less than or equal to rho. Which is less than modulus of z minus z naught, which is less than sigma, which is less than or equal to infinity. So here's a typical point z, and the center of this is z naught. All right. What else? What's the Laurent decomposition? Laurent decomposition is something like f of z equals to f0 of z plus f1 of z, where, what's the deal? This f0 is, what is that? That's holomorphic on what? On the disk of radius sigma, centered at z naught, yeah. And f1 is element is holomorphic on the set. I don't have a notation for this, so I'll write it down. Z such that the modulus of z minus z naught is, well, greater than rho. Right, so on that exterior annulus, F1 is analytic. All right, and if we insist that F1 of infinity is 0, then this decomposition is unique. All right. In fact, insisting that F1 was infinity is what would have given us the uniqueness. The thing I was a little bit waffling on at the end of last class, like why does that thing go to 0? It's because you're looking at the thing we were looking at and arguing went to 0 was h. As z goes to infinity, h of z is g1 of z minus f1 of z. But g1 of z and f1 of z both are limiting to g1 of infinity and f1 of infinity. G1 of infinity and f1 of infinity in our last class. And those were both, by assumption, 0. So you get 0 minus 0, which is just 0. So that's why h of z should be been limiting to 0 as h went to infinity. And then that is part of how we argued that the Laurent decomposition was unique. Now, the existence then is still up to us to show. And so what I say here is that the existence of the Laurent decomposition is due to Cauchy's integral formula on the annulus. And I said, well, technically we haven't shown this result explicitly yet. We need to use the crosscut idea, which is illustrated somewhere else, but let's illustrate it here. So what we need to do is we need to look at a subannulus, and let me look at a subannulus. So a subannulus is something like this. And I think I call the outer radius of the subannulus, what do I call that one? That one I call S. And then a little bit beyond rho, we'll put T, I think. So just to, oh, actually I used R for that one. So sorry, not T, but R. So the inequalities here, if you're keeping track, are 0, less than or equal to rho, less than R, less than S, less than, what's the last one? Sigma, which is less than or equal to infinity. So the point is to find a subannulus. It's an annulus inside the annulus, all right? And I'm going to, I say, my claim is that we can apply Cauchy's integral formula on this subannulus, all right? So let's try to do that. Now I say you can make a crosscut. So what I'm saying there is what we'll do is take this big region between the red and the green circles, and we'll just put some crosscuts like this. Now the reason I do that is why. So let's see here. Counterclockwise, we go like that, right? We go like this. And so we'll use the top of the crosscut like that, and then like this, downstairs, like this, like this, like this, like that. So the brown arrows, what I'm doing is I'm illustrating if you just look at the top half or the bottom half of the annulus, you can think about them separately as what? I'll draw them again over here. See, these are simply connected, right? Regions, so we can apply the Cauchy's integral formula, right? In fact, I think I talked about Cauchy's integral formula for regions with holes before. At least I talked about something with holes before. I can't remember exactly, but let's just make this discussion self-contained. Suppose you only knew Cauchy's integral formula for a simply connected region. Here's how you could take this subannulus and turn it into two simply connected regions. And why would that be interesting? Because what's Cauchy's integral formula tell you? Well, here's what I argue. So let's see if we can understand this step here. I say that by applying Cauchy's integral formula to each one of these, we get the following. We get f of z is equal to 1 over 2 pi I, the integral. It's around a closed loop here, modulus of w minus z naught equal to s, f of w dw over w minus z minus 1 over 2 pi I, the integral over modulus of w minus z naught equals to r, f of w dw over w minus z. Let's see here. So where is z in all this? I say z is subject to the condition rho less than r less than modulus of z minus z naught less than s less than sigma. So z is in the subannulus. So what did Cauchy's integral formula tell us before? It was what? We had some region, right? And we had that the integral over the boundary of the region of f of w dw over w minus z was equal to what? 2 pi I f of, well, let's say z naught, right? What is the conditions needed for that to be true? What do we need? We needed that f was what? F is what? Well, but f is a function. So z naught's got to be in here somewhere. Fair enough. But we also needed that f was holomorphic on R, right? So like, the trouble of the integration is completely encapsulated in the division by something that could be 0. When, of course, when w is equal to z naught, right? Now, admittedly, that's not actually, I'm not saying that the integration actually gets to that point, but we've learned that that's where the non-trivial integration is coming from, is the fact that there's a singularity inside the loop. All right, that's something we're starting to understand. Okay, but anyway, whether or not reasons aside, this is something we've proved, right? Cauchy's integral formula. And so how is it that, how am I applying it over here? So let's see here. This is CR, this is CR south, this is CR north, this is CS north, this is, oh, this is stupid. Let me use plus and, sorry, I'm going to have to use plus and minus because I've already used S for, you see why. I was about to use CSS, which, I mean, fine, you could, but whatever. Anyway, the lower and upper half. And so my point to you guys is that, let's see here, this outer edge, and both of these, by the way, are taken to be counterclockwise. These are both counterclockwise, is the assumption. There might be actually a little arrow on these if you looked closely. But the point is that this first one is really what? It's the union of CS minus and CS plus, right? And the second one is actually minus CR minus union minus CR plus because they're disoriented. You see the inner circle as it's picked up from the crosscut. Well, anyway, the positive orientation for the whole is clockwise. So it's opposite the the counterclockwise orientation. You might just give the circle CR in the absence of this larger discussion. And so you see what's going on here is you could add these together, and what do you get? Over what? Right, it's over the union, over everything, right? Over this one, that one. This minus and that minus has come together to give me a plus. So I'm really looking at the union of the whole, I don't know what to call it. Goodness gracious, I need to name. Let's say boundary of this thing. Okay.
So this isn't really just about some vectors, right? Because if Z is in one of these
Or does it?
I mean, I assume that it works out anyway, but
Well, that's the thing, is if z is in the upper half, then the lower half is, what happens if z is in the upper half? What can you say about the expression f of w over w minus z? If z is in the upper half, then f of w over w minus z is simply holomorphic on the whole lower half. And vice versa. So wherever z isn't, the integral is 0. So I think you're just adding 0. I don't think that's a problem. So the larger point anyway is that Cauchy's integral formula gives us this decomposition of this integral into these two pieces if you look at it. And then here's where it gets interesting is we identify that the two integrals that I've written down are the f0 and f1. So which of these two integrals serve as f0 and which one of these serve as f1? Say the blue one or the pink one. What do you guys think? Which one of these is going to be holomorphic? So allegedly one of these is going to be holomorphic inside the green circle, and the other one's going to be holomorphic outside the red circle. Which one is holomorphic inside the green circle? What's that? The blue one? And why is that? Because it's S.
actually, wait, no, I changed my mind.
Why? I mean, why would the blue one be holomorphic? You don't know. So your initial guess agrees with my notes. I say that the first one is the f0. And this one over here is the f1 of z.
Why don't both?
So I said f0, notice f0 is analytic for z minus z naught less than s. Why is that true? Why is that analytic for z minus z naught less than s? I mean, I suppose it's because for z minus z naught less than s, we don't get an infinity plugged into the path, right? I mean, like this integral, we can do it, and that integral is holomorphic because, well, f is assumed to be holomorphic. Where? Well, that's not the argument. But anyway, I mean, if z minus z naught is less than s, that means we don't actually get division by 0 here. And we're just integrating a holomorphic function over something which doesn't go to 0, which we can argue is holomorphic. On the other hand, over here, why would we get into trouble over there if we... I'm sorry, guys. I'm just...
Are you talking about between R and S or between rho and sigma?
Between R and S.
Oh.
Yeah. But the point is S is arbitrary, so you can let S kind of like edge out to sigma, and you can let the R shrink down to rho after you do it for arbitrary R and S. Yeah. And so we get the Laurent decomposition on the annulus. Anyway, through something which is not that complicated, you can argue that the pink one, let's see here, Z minus W, good grief, modulus of Z minus Z naught equal to R would be here, right? And so if we're looking at Z, which is outside of the red circle, then we don't cross the divergence of the integrand, and the pink one is what it basically, I think that's all that it is, really. Just the formula that you're integrating is something which is the thing that's bothering me is like I don't know about F outside of the annulus, so I don't want to be careful to overstate it.
But we're never evaluating F outside of the annulus.
That's good point. Good point. So, right. All right. I'm going to go on since I'm not adding any value to the course here at the moment. So, an example. So here I have f of z equal to 2z minus I over z times z minus I. All right, and so this is holomorphic where on C removing what you got to get rid of I, and 0 and I are trouble points, but other than that, right, any other point we give complex differentiability any other points than those two. And you can calculate that f of z is actually equal to 1 over z plus 1 over z minus I. If you don't believe me, we could just make a common denominator and see if we get back, to the same thing again. I'm a little bit worried to do it at the moment, but so I get z minus I plus z. Okay, yeah, it works. Okay, I don't. Okay, so with respect to the annulus, 0 less than z less than 1, let's see here. So grief. So I say we have f0. Let's see here. Let me put the, goodness gracious. So I want to think about the Laurent decomposition with respect to some annulus here. Yeah? Just think about it. See if we can see it. So we got here centered at 0. This is a sort of degenerate annulus with the outer radius being 1, the inner radius just being the point removed. Kind of a silly case, but an annulus nonetheless. And if you look at f, what's the f0, what's the f1? So in here we have f0 of z is what? Which part is holomorphic from the outer edge to the inside? It's 1 over z minus I, right? I mean, minus I is down here, but that's outside the scope of this annulus. It's on the edge. So the 0th piece is 1 over z minus I. On the other hand, f1 is what? 1 over z. Because that is singular at the origin, and on the other hand, it goes to 0 as we go to infinity, It's definitely holomorphic, outside of the inner circle there. So that is already a Laurent decomposition on the deleted unit disk. Okay? Again, this is my F1, and this is my F0. So what's next? We could try to look at the Laurent decompositions. Yep.
Why did you look at minus
Oh, because I don't know math. So it should have been I. Yeah, thank you. Good question. So what I'm learning is I should not take questions during convocation ever, because then I don't get time to prepare for class, and then this happens. All right, so I is up there. All right, so then, although sometimes preparing for class a lot also ruins my lecture, I don't know. So you go figure. All right, so on the other hand, I say for the annulus, we could look at a different annulus, right? I'll draw a separate picture because it would get too cluttered if I did it on the same picture, but you could try to do it on the same picture. I'll do it over here though. So with respect to I, you can look at the, like here's 0. So let's look at the punctured annulus. 0 less than modulus of z minus I less than 1. So the outer edge is a unit circle, radius 1, and we're puncturing the inside. In this context, notice that the tables have turned. In this case, we still have the Laurent decomposition, right? In this one, actually, f0 of z is 1 over z. Because 1 over z is holomorphic inside here, right? The singularity is at the edge down here on this annulus, centered at I. But on the other hand, F1 is 1 over z minus I. So there's a couple of Laurent decompositions. Pretty simple, but there it is. We could look at a more complicated example. Sorry, whatever I'm failing to verbalize here in this proof, it's something minor. So I'm pretty sure it's bothering me, but I must go on. All right. So this one is a little bit tougher. Here, the next example that I have is f of z 1 over sine z. All right. And I said this has a Laurent decomposition on the annuli which fit between successive zeros of sine z. So this has singularities where? Yeah, integer multiples of pi, right? So I said, so we could do sine of z is z minus 1/6 z cubed. And if I want to, I could look at f of z 1 over sine z. And I could rewrite that as, say, 1 over z times 1 over 1 minus 1/6 z squared. Yeah. Factor out the z. And then do geometric on that. That would give me 1 over z times 1 plus z squared over 6 plus ... All right? And so that would give me 1 over z plus z over 6 plus ... And if I look at the origin, deleted, and then an annulus out to radius pi, right? So this would be my f1 of z. And this, if you can compute more if you wanted to, but here you go, here's f0 of z. So the f1 of z is not analytic on the disk of radius pi, right? But it is analytic outside, away from, on the exterior and on the punctured plane, really. And f0, on the other hand, is analytic inside the disk of radius pi. And so we have 0 less than modulus of z less than pi is the annulus I'm talking about here. That's the Laurent decomposition. Question? You seem like you have a question. I think he's... Yes?
Which one did you say was analytic?
Well, you tell me. Which one of these expressions, 1 over z, where is that analytic? Yeah, for z not equal to 0, so that would be, the outside of the inner circle here. The inner circle for this annulus is very silly. It's just the origin, right? And on the other hand, z over 6 plus higher order terms with z, that's going to end up, that's going to be analytic inside the disk, actually. All right, so there's a larger point to make here, which is that if we have a Laurent decomposition, we can find a power series. So there's two things to put together here, right? So f0 of z being analytic inside the disk of radius sigma gives us what? f0 is equal to the sum k equals 0 to infinity of a sub k times z minus z naught to the k. Yeah? So this is, because f0 is holomorphic on the disk of radius, what we got? Sigma, I suppose, centered at z naught, right? But on the other hand, we also know that f1 is analytic where? For z minus z naught greater than rho, right? We have that f1 is analytic. In other words, f1 is analytic at infinity, and we learned that means that you can write that as the sum, well, let's say k equals 0 to infinity of a sub, well, I probably should use a different letter here. I'll use a b for the moment, b sub k divided by z minus z naught to the k, right? But what else did we assume about the Laurent decomposition? We assumed that as you go to infinity, the f1 piece goes to 0, right? So if you plug in k equals to 0 for the b terms, what should the b sub 0 be? By assumption, we're saying when you're really, really far out, this goes to 0, or more quickly f1 of infinity equals to 0. That tells me that my b0 should be 0. So I can just rewrite this as the sum k equals 1 to infinity of b sub k over z minus z naught to the k. Or, just to make things more symmetrical, we could write that as the sum k equals minus 1 to infinity, minus infinity of a sub k times z minus z naught to the k. Because you're just going from the minus 1 power to minus infinity, and we have not given a meaning to a with negative coefficients yet. So why not? Well, anyway, so altogether, what do we got? We have that f of z is the sum k equals minus infinity to infinity of a sub k times z minus z naught to the k. And this sort of thing is called a Laurent series. Where does this series converge? It's where both of these things make sense, right? Which is sigma less than modulus of z minus z naught. Actually, I've lost my picture. I've lost my inequalities. Which one? Rho was on the bottom, sigma's on top. Is that right? Yeah. So this is the Laurent series decomposition of a function. To capture singularities inside the annulus, we just throw in reciprocal powers. But it's so much more than that, because what's really neat is if you take this thing and you integrate it, something really cool happens. What happens if we integrate the Laurent series decomposition for f? So let's take the integral over a circle somewhere inside the annulus of its application. So z minus z naught equals to r, circle, f of z dz. All right, so this gives us the integral sum k equals minus infinity to infinity of a sub k times z minus z naught to the power k dz. Then, good news, these are uniformly convergent series of holomorphic functions, and as such, I am well within my rights to exchange the order of integration and summation and do integration term by term, which is ever so lovely, because then we just get back to that basic integral we did back in the day, right, of just the power function. And how does that work out? Integral of z minus z naught to the power k dz over the circle centered at z naught. How's that calculation work out? By the way, very popular test 2 question. Calculate that integral, since you guys are asking me. So to calculate the integral, you just parameterize, work it out. And in almost every case, it just works out to 0, except for one special case, which is k equals to minus 1. K equals to minus 1 is the one time that this doesn't work out to 0. So in short, when you do the calculation, what you get is a sub k times 2 pi I Kronecker delta of k comma minus 1, which is just a way of me saying that the integral is 0, except when it's not. When is it not? At k equals to minus 1, in which case we get 2 pi I. And that means that that infinite, well, doubly infinite sum collapses down to just one term. In particular, 2 pi I a to the minus 1. By the way, the minus 1th coefficient of the Laurent series is called the residue of f. A minus 1 is the residue of f of z centered at z equals to z naught. Now I will tell you all of the really neat, quick, gory calculational tricks about residues after test 2. And they're not bad. At the moment, we're just going to operate, though, in terms of direct computation using the geometric series and direct calculation, series calculations to arrive at residues. Well, we're not even really going to think of them as residues so much as we are going to think of this as a theorem. And the theorem simply says this. What's the theorem say? It says that if you want to integrate, over the circle of radius r centered at z naught, f of z dz, then it's just equal to 2 pi I a to the minus 1 given the notation that I have on the middle board. All right. Now, So my next example is my next example is kind of interesting. Essentially over the next page of notes or so, what I argue is, if you could do this for f, you could just as well do it for what? Like f of z divided by z minus z naught to the n power. Right? And when you do that, well, anyway, I'm not sure the next example. The next example is interesting, but I think I'll let you read it. I don't think it's that crucial to us here. Oh, stink. Sorry, I need to write something. So in short, I get the larger question is, what are the values of a sub k? All right? I mean, we just figured out that a minus 1 gives you the integral, right? So the natural question to ask, that's the question I asked in the notes, I just failed to remember the question, which is, well, what about the other coefficients? What integrals are those related to, if any? All right? And so the answer there is, let's see here. So likewise, and the example I skipped over basically was just to motivate this calculation. That's all. Example 11.1.7 is interesting. Maybe I should do it. Maybe I should. All right. This to the n plus 1. Circle centered at circle radius r, centered at z naught. This is equal to what? The integral over the circle. And then you trade f for its Laurent decomposition, Laurent series. So you've got a sub k times what? So this time, we don't just have z minus z naught to the k, we have z minus z naught to the what? K minus n minus 1, right? So then you flip the integration in the summation and apply the Kronecker delta result that the integral term by term only works out when the power is to the minus 1 power. When is this minus 1? K equals to n, right? So this simplifies to 2 pi I a sub n. By the same calculation I just went through. And so therefore, a sub n, or if you like, a sub k, is going to be equal to what? Well, 1 over 2 pi I integral of f of z dz over z minus z naught to the dk plus 1. And that, of course, is for the circle, radius r. And all of this is happening where? This is happening on some annulus where the Laurent series decomposition for the function is given. Right? But on that annulus, integrals of the function, or integrals of the function divided by z minus z naught to the k plus 1, they're given to us simply by selecting appropriate coefficients in the Laurent decomposition. So the Laurent decomposition, the Laurent series rather, right? The Laurent series, the coefficients in the series reveal integrals of the function around circles in the domain for which the series decomposition exists. Let me put that in other words. We can calculate an integral of a function, possibly by finding its Laurent series decomposition and just reading off the coefficient of one term in the series in the appropriate circumstance and context. This is really quite amazing, right? And that's the heart of the residue calculus, which we will go on and cover more of. Now, the next section, so I think that this is kind of, we get this far, and then we'll come back to residues in chapter 12, all right? At this point, we change gears and we start talking about, just rather than applying the Laurent series decomposition, we start analyzing it as it relates to the problem of singularities, all right? So the next, I keep looking for my watch, which I left at home, because I'm an idiot. The next arc of the course, next section in the course is about different kinds of singularities. So let me show you. There are three kinds of singularities. So-called, what's an isolated singularity of a function? So Z naught is an isolated singularity of F if F is holomorphic on, well, at each Z not equal to Z naught in some disk. Modulus of Z minus Z naught less than epsilon, right? I mean, the point is, it's isolated. If it's isolated, I mean, you can find some little disk on which there's no other singularities, all right? Or another way of saying this would be, say, F is analytic on the punctured disk, all right, of radius epsilon. And so then there are, so great. We just proved that there's a Laurent decomposition, right, on a punctured disk, because that's an annulus. So if you look at that, that means we can look at the Laurent series centered at Z naught for this isolated singularity. And if you think about it logically, there are three possibilities. Here are those three possibilities. What are the three cases? Number one, f of z equal to sum k equals 0 to infinity of a sub k times z minus z naught to the k. Number two, f of z equal to the sum k equals minus n to infinity a sub k z minus z naught to the k. Number three, and this is the bad one, f of z equals the sum k equals minus infinity to infinity of a to the k times z minus z naught to the k, where a sub k is not equal to 0 for infinitely many coefficients with k less than 0. Whoa. So each one of these has a name. I'll give you an example of each too. All right? So case number one would be something like f of z equals the sine of z over z. This has z equals to 0 as a isolated singularity. In fact, it's its only singularity. And if you calculate the Laurent series expansion, it's exactly 1 minus 1/6 z squared plus dot dot dot. Because all I did was just cancel out the z in the power series expansion for sine with 1 over z. There you go, that's the Laurent series expansion. As you can see, it's just straight up holomorphic on the disk, actually. So this is what's called a hole in the graph. No, here we call it a removable singularity, because removing it is as simple as just canceling out the term like I did. 2 would be something like f of z equals to, 1 over, well, let's see here, 1 over, 1 over z plus e to the z, just to make it really simple. This would give you, by the way, this means it's what's called a pole of order n. So this is pole of order 1, also called a simple pole. Much like we used the term simple zero before. Now we talk about simple pole. We also talk about a double pole. But anyway, a pole means that the Laurent series has only finitely many reciprocal terms, non-trivially enter the expansion. On the other hand, part number 3, this is a so-called essential singularity. These are unpleasant. And weird things are true about them. So e to the 1 over z. This has an essential singularity at 0. If you look at the power series expansion, you got yourself 1 plus 1 over z plus 1 over 2z squared plus da da da. There are infinitely many reciprocal terms in that. This is an essential singularity. Fun theorem. For an essential singularity, if you look at a little open disk close to the essential singularity, you will find that the complex function takes on almost every value of the complex plane except 1. I mean, this is an exponential. It doesn't take on the value 0. But every other value you can show it takes on. That's kind of messed up, right? So anyway, we're going to study these 3 different kinds of singularities, talk about their properties and what that has to do with the function being unbounded and so forth. And I will tell you my favorite joke next class. So anyway, see you guys.